Welcome to the week 2 vocabulary list. And we talked about motion, we're getting into forces. There's a lot of relationship between these two concepts. When you think about forcing something, usually means you're pushing or pulling or trying to twist a cap off. A force is a push or a pull. It has quantity and it has direction. It can be either a push or a pull. Some of these are visible, some, like gravity, are invisible. The unit of force is the Newton. We need to have units. So if I say there was a force pushed against something, how much force was it? Well, we call those newtons. And this was named after Isaac Newton. He was a great scientist of his time, one of the smartest people ever to work in science, really. And the old story was he was sitting under an apple tree, an apple fell on his head, and he discovered gravity. Now, it's a silly story. People knew that things fell long before Isaac Newton. That was not the first time it occurred to him that things fell. But he did come up with some of the ideas of gravity. And in honor of that, we named the force of the unit of force after him. And 1 Newton, to give you an idea, ironically enough, is about the force you would get if you took an apple, lifted it about 1 meter off the ground, that's about 3 feet, and dropped it. When it hit the ground, it would have a force of approximately 1 Newton. Anytime they ask you a question and they say, what is the force? You calculate it, make sure your answer is in newtons. So, for example, it turns out weight is actually scientifically, we usually use pounds and ounces and stuff, but scientifically, weight is a force. It's the force of gravity acting on a mass, and it should be measured in newtons. I personally don't know what my weight in newtons is because I don't need to, but that's really how things are measured. Now, net force is what you're left with once you cancel out all the forces that are acting against each other. So right now, the net force of me is pretty much 0. Gravity is pushing down on me, but the floor is pushing up on my chair just as much as gravity is pushing it down. And you know this because if the floor were pushing up harder than gravity, I'd be rising up in the air. And if gravity were pushing harder than the floor was pushing back, I'd be sinking into it. So I'm sitting still. But here's an example where you could calculate a net force. Here's 2 people, maybe not the smartest folks. They're trying to move a box, but miscommunication. They're moving in opposite directions. One guy is pushing with a force of 8 newtons. He's trying to get to the right. And the stronger fellow is pushing in the other direction toward the left with a force of 12 newtons. Now, because he is pushing harder than the other guy, the net force would be if I subtract these 2. He's pushing with 12, so 12 minus 8. The net force is 4 newtons toward the left. Force is a vector quantity. It has both magnitude and direction. If they were smart and they both got on the same side and were pushing, then we would add those 2 up. Then there would be a net force of 12 and 8. It would be 20 newtons going presumably toward the left, and they'd be moving a whole lot faster. Now, we are ignoring some factors here. Like when you're pushing a box across the floor, there are forces that will actually work against you. It's not that easy. We're kind of pretending that there's no friction here, and that's our next term, which is friction. Friction is a force. Anytime 2 objects are touching each other, there is friction. Friction works against motion. So if you're pushing in one direction, friction is pushing in the other direction. It's the reason why if you start something moving and you stop pushing it, it will eventually slow down and stop. Friction will have canceled out any effort that you put in there. The less friction you have, the longer that might take. So if you were to, throw a bowling ball down a glass or icy frozen lake, that bowling ball would go for a long time because ice doesn't have a lot of friction. It would eventually stop. If you were to throw that same bowling ball down a dirt road, it would stop real fast because dirt has way more friction than ice does. It's one reason why if you're driving in a car, you'd probably rather be on a dirt road than an icy road. Sometimes if the friction is too small, you're trying to turn your car and your car keeps right on going in a straight line. We'll be talking a lot more about that idea. There's different kinds of friction. And you may have noticed when you try to move something heavy, At first, it's really hard to get it moving. And once you get it moving, it's easier to keep it going. But if you stop, then it's hard to get it moving again. And that's because of a thing called static friction. Static friction is the friction between two objects that are not moving. You have to break the static friction before you can get any motion at all. And the reason there's static friction is because although things might seem smooth, here's a wooden box, and let's say they sanded the wood. The wood's pretty smooth on the bottom, and the floor is pretty smooth, or it seems to be. But if you could shrink down to the size of atoms and look at it, there's actually all kinds of divots and grooves, and they get locked together, and you've got to actually break that. You've got to break these places where they're locked together to get it to move in the first place. So static friction is the strongest friction. Static means standing still. Once you get it moving, now you're into a new friction, sliding friction. Sliding friction is a lot less than static friction was. It's still a reasonably strong friction, though. And to make things better, you try to make the surfaces as smooth as they can be as they're sliding by. So the skier, for example, might wax their skis, put a layer of wax on it. Wax is an oil, so it kind of makes it slick and lets them go over the snow way better. If they were to hit an ice patch with their wax skis, they might wish they had a little more friction because now zoom, off you go, and it's kind of hard to steer. And that's an important concept. Sometimes you want to have friction, like when you are trying to walk. Imagine if you were on a floor that was totally slicked up with oil. You might be kind of like a cartoon character trying to move and your feet are going, but you're not getting very far. You'd probably slip and fall. If you're trying to warm up your hands, when you rub them together, the more friction you have, the more heat it generates. And then there are some times when you don't want to have a lot of friction. You put oil in your car to keep the engine parts that are moving from rubbing together and making too much heat and actually cracking the engine block. Another thing we discovered a long time ago was the wheel. And the wheel works because it minimizes the friction between the objects that we're trying to move here. If I was to try to drag a car without wheels, that would be almost impossible. It would just be dragging on the ground. The sliding friction would be awful. But you put it on wheels, and now notice how the wheel is not a whole lot of it is touching the ground. It's only in that one little area, and it's rolling over, not sliding over. So this rolling friction is actually a very weak form of friction. Yes, it will eventually slow down. If you're in a car and you're going at a good speed and you take your foot off the gas pedal on a flat road, you will slow down and eventually stop. But it takes a while for the rolling friction to do that. Now, if you apply your brakes, you slam on your brakes, now you've locked your wheels. They're not spinning anymore, and you're screaming over the pavement, creating, all kinds of sounds and smells and screams and everything. That's suddenly turned into sliding friction, which is stronger than rolling friction. So you'll come to a stop a whole lot faster than just taking your foot off the gas pedal. And then the last kind of friction is fluid friction. Fluid friction is when you are moving through a fluid. Now, most people think fluids mean liquids, and that is a fluid, but so is a gas. A fluid is a thing that flows. So when you stick your hand out the window, you feel that air slamming against you. That's a kind of fluid friction. Cars are designed to minimize that, let the air go over as easily as possible so that they can go faster. And this idea of the air here is air resistance. Air resistance is the friction force of air against a moving object. And it's the reason why, we mentioned this last week, if you jump out of an airplane and you start falling, you go faster and faster and faster until you get to a speed where you're going so fast that the air is hitting you with as much force as gravity is pushing against you, pulling you down toward the earth. And you don't stop, but you stay at that speed. For an average human being, it's about 120 miles an hour. That's your air resistance. You don't really want to hit the ground at 120 miles an hour. People have survived, but not many. So you pull your parachute. Now, when your parachute goes up, suddenly you have increased the amount of air resistance pushing against you. Before it was just the air hitting your body. Now it's the air hitting your body and hitting that big giant parachute, which hasn't, added any weight to you. So you slow down to, 20, 15 miles an hour, and that should allow you to hit the ground at a survivable rate. Our last word here is a pretty important one, is gravity. Gravity is a force that acts between any two objects. Every object in the universe is attracted to you, and you are attracted to it. The reason you don't notice any of that is because the rule of gravity is this: the bigger an object is, the more gravity it has. Big objects have a lot of gravity, small objects have less gravity. The closer an object is, the stronger the gravity between the two objects. So when you think about where you are right now, the biggest, closest object to you is the planet Earth. It's not as big as the sun. The sun's a million times bigger, but the sun is 93 million miles away. It does attract you, but not to any significant level. So if you jump up in the air, the gravitational pull of the Earth on you and you on the Earth takes you right back down. And this explains something that a lot of people seem to think: if you were to go to the bottom of the Earth, the blood would rush to your head. They wonder, how do people live down there? No matter where you are in the Earth, there is really no up or down. Okay? Wherever you are in the Earth is pulling you toward the center. So if you're at the bottom of the Earth, let's say you're in Australia, you don't feel the blood rush to your head because the blood is being pulled toward the bottom of your feet, just like it is right here in Sanford. No matter where you go, when you drop that ball, it's going to hit the ground. It is all being pulled to the same area. That's how gravity works. So these are basic vocabulary concepts for this week. Please go take the vocabulary quiz, pretty easy one. And I will see you all tomorrow. Take care. Bye now.